A very important problem in dynamics, one which has got a long history and which is absolutely crucial to the study of dynamics, is the so called two body central force problem. If you recall, we had mentioned the last time that we could regard the gravitational force between two particles as arising from a certain gravitational potential which depended on the product of their masses multiplied by gravitational constant divided by the distance between these two particles. That led to the inverse square law of force between these two particles, the gravitational force. Now the general two body central force problem is as follows. You have two particles of masses m1 and m2 with some prescribed momenta to start with, and then the question is, if they interact with each other through a central force, namely a force which is directed along the line joining these two particles and which is derived from some kind of potential, then can we solve for all the dynamical variables in this problem, namely can we find the coordinates, instantaneous coordinates r1 and r2 of these particles, can we find the instantaneous momenta p1 and p2 of these particles. So given the fact that some initial conditions, initial coordinates are given, can we find all these dynamical variables as functions of time. In particular, if they should go into some kind of periodic motion around their common center of mass, can we deduce this or not. So that is the general two body central force problem, and what I shall do is to show you the steps by which this problem is approached, not necessarily solve it in the most general case, but then we will specialize to the case of the Kepler problem. So after showing that this two body problem is essentially a one body problem in a certain specific sense, I will show that the problem in the case of the Kepler problem, namely the gravitational force between two particles, this leads to orbits, the very familiar Kepler's laws of motion and so on. So this will be our goal, to try to understand how this happens starting from first principles. Now the first thing that we have is that the total energy of the system, of this system of two particles, and there is nothing else in the universe, just these two particles moving slow compared to the speed of light in vacuum, so it is non-relativistic. The total energy is the kinetic energy of the two particles plus the potential energy of the two particles. And we believe that because time is homogeneous, there is nothing to specify what the origin of time is one way or another. We believe that we can prove that the total energy is a constant of the motion, and this is given by the sum of kinetic energies. So it is P1 squared over twice m1 plus P2 squared over twice m2. These are the squares of the magnitudes of these two vectors plus a potential energy which we will now assume to be the following. We will assume this to be a function v, not of the general coordinates r1 and r2, no, but rather a function v of the distance between the two of them. So instead of v as a general function of r1 and r2, we have a potential energy in this case which depends only on the distance between the two particles. The actual orientation of this vector r1 minus r2 is irrelevant. So not only are we saying that the absolute origin of space coordinates does not matter, it is only a difference between the two vectors r1 and r2 that matters. We are going further and saying that the energy of interaction, the potential energy of these two particles, is a function only of the distance between the two particles and nothing else. So under such a situation, given this total energy, we would like to deduce from the equations of motion, which we can write down, Newton's second law of motion. For each of the particles, we can try to write down what the equations of motion are and try to solve them given some specific conditions. Now that is a very general problem. In general, it is not easy to write down explicit solutions to these equations of motion, but a very great simplifying fact arises as soon as we say that the potential energy is a function only of the distance between the two particles. It immediately suggests that we should not use the coordinates r1, r2, p1 and p2, but rather a coordinate which specifically is a linear combination of r1 and r2 in the following sense. So, from r1, r2, p1, p2, from this set of variables one goes to a new set of variables, also the same in number finally, because you are not eliminating any variables, which takes into account the fact that what appears here is only a function of the difference, only a function of the magnitude of the relative coordinate r1 minus r2 between these two particles. And these new coordinates are the following. One uses capital R, little r, a capital P corresponding to capital R, and a little p, which have the following properties. This coordinate capital R, little r, is by definition r1 minus r2, and that is the relative coordinate, and capital R is the coordinate, not surprisingly, of the center of mass of the two particles. So, with respect to any origin whatsoever, you define a center of mass coordinate which is m1 r1. So, it is the coordinate of the first particle weighted with its mass plus m2 r2 divided by m1 plus m2. If the two masses are equal, m1 equal to m2, then this is the halfway point, r1 plus r2 divided by 2. Otherwise, this is the general expression for the coordinate of the center of mass. So, center of coordinate. So, instead of the vectors little r1 and little r2, one uses two new linear combinations of these vectors, one of which is the relative coordinate and the other is the center of mass coordinate. Now, it is immediately clear that I could have defined the relative coordinate as r2 minus r1, it will not make a difference, and basically that is because this is only a function of the magnitude of this vector, its absolute sign does not matter at all. Okay. Corresponding to those two coordinate vectors, there are two momentum vectors, and in this case it turns out, and I will justify why this should be so, the total momentum p1 plus p2, this is the total momentum, linear momentum vector, and little p is the relative momentum little p. It is not equal to p1 minus p2 or p2 minus p1, it is rather equal to m2 p1 minus m1 p2, and it is called the relative momentum. Divided by. It should have the dimensions of a linear momentum, so there is a division here by the total mass here. Now, there is a technical reason, or rather there is a systematic procedure by which one can arrive at the conclusion that the relative momentum is this combination and not any other combination. The total momentum is fairly straightforward. Now, the point is that when you write the total energy down in this way, there is a method by which, given the total energy, it is called the Hamiltonian in this case, there is a way of writing down Newton's equations or the equations of motion from this total energy, exploiting the fact that it is this thing here is a function only of the magnitude of the relative coordinate here. Then it is straightforward to show that these are the combinations, the right combinations that may be chosen, and as you would have guessed by now, since this entire system is not being acted upon by any external force anywhere or any external torque, it is immediately clear from what we have said earlier that one expects this momentum to be a constant of the motion, because by Newton's third law, the force exerted on particle 1 by particle 2 will be equal and opposite to the force exerted by particle 2 on particle 1, and as we saw, that immediately implies that the sum of the two momenta in the two body problem is a constant of the motion. So this one here is a constant of the motion, a constant of the motion. Just as the energy itself is a constant of the motion, because the whole thing is homogeneous in time, there is no reference to any origin, any t equal to 0 instant, any special instant, therefore energy is also conserved. So we have at our hands the statement that the momentum, the total momentum is conserved, the energy is conserved, and then given this fact, given these changes of variables, what we have to do is to go back and rewrite the total energy in terms of these new variables. So all we have done is to change from little r1, little r2, little p1, little p2 to capital R, little r, capital P, little p with linear combinations. One can invert those relations and solve for the original variables in terms of the new ones and substitute in here, and then what happens is the following. This becomes equal to, and this is a piece of algebra which is easily carried out, it becomes equal to p squared over twice m plus little p squared over twice mu, and I explain what mu is in a minute, plus v of little r, because now this vector is little r and its magnitude is little r without an arrow up there. So this total energy reduces to this expression here, where capital M is the sum of the masses, and that is the total mass, and little mu is equal to m1 m2 over m1 plus m2 equal to the so called reduced mass. This fashion. So we have explicitly here an expression for the total energy in terms of the total momentum, the relative momentum, and a potential function, a potential energy which depends only on the magnitude of the relative coordinate. It is immediately obvious by inspection that this coordinate, the center of mass coordinate, does not appear anywhere here. It does not appear in the expression of the total energy at all. And then of course it follows that just as the total momentum is a constant, it follows that this coordinate, which could be regarded as defining the coordinate of a particle which is with the total mass with momentum capital P, which is a constant of the motion, is like a free particle. So it is as if you have a different problem now. The original problem of masses m1 and m2 has been reduced to the problem of a capital M particle of mass capital M moving at a constant momentum capital P, like a free particle in a straight line, together with the problem of another particle of effective mass little mu with momentum little p moving in a central potential V of r. So these two problems have got decoupled, and once that is done, this problem reduces and simplifies. As a consequence, if I wrote these equations down for the rate of change of these coordinates and so on, it turns out then that dp over dt equal to 0, and I shan't write down exactly how this is derived from the total energy, but it is fairly straightforward to do this. So this will imply that P equal to a constant of the motion, and dP over dt, the rate of change of this thing here, is equal to, by Newton's third law, by Newton's second law, it is equal to the force seen by this particle would be derived from this potential, and that is a central potential. So this becomes equal to minus dV r over dr times E sub r. So the problem involving little r and little p is isolated from the problem involving capital P. And this will also imply immediately that this coordinate r of t, by integrating this equation out, r of t is equal to r of 0 plus whatever a free particle does with a given initial momentum and a mass. So this is p times t over m. So we have a complete solution for what the center of mass does. It moves linearly, so this whole system, its center of mass with an effective total mass equal to m1 plus m2 moves in a straight line depending on what the initial conditions were. So if you specify for me the initial momenta of these two particles, I know this and I know the mass, and if you tell me where the center of mass was located initially, I know where it is located at any further instant of time. So this part of the problem is like a free particle and is solved trivially by the laws of motion being explicitly integrated out. It leaves us with this problem here. That is the central force problem. The problem of a particle of effective mass mu in a central force or central potential V of r. And now of course you have to tell me what this V of r is in order for me to make progress, to make further progress and say what kind of motion we expect of this. Now we need initial conditions for this. So you need to know what is the initial coordinates of these two, and you need to know the initial values here. The sum of them remains constant, and then it is a question of how these quantities evolve as a function of time. Specifically, we would like to know what is r of t. Given r of 0, what is this r of t, and of course what is this variable p of t equal to. So this is the central force problem, the one body central force problem, because we now have a particle whose effective mass is mu, the reduced mass, and we would like to know what it does here. Now notice something about this reduced mass. Notice that if m1 is much greater than m2, so one of the particles is very much larger, very much massive, more massive than the other one, then mu is approximately equal to, you can neglect this m2 compared to this m1, the m1 cancels out, then this is approximately equal to m2. This is what happens, for instance, if you consider any of the planets moving around the sun. So if the mass of the sun is m1 and the mass of the planet is m2, the effective motion of this planet is like that of a body of mass, effectively that of the planet itself. The mass of the sun cancels out top and bottom, and you have effectively a reduced mass, which is essentially the mass of the planet itself. And in this case, it is also clear that if m1 is much bigger than m2, then just as you can neglect this m2 compared to this m1, you can neglect this compared to that, and the center of mass coordinate is essentially the coordinate of the very much heavier particle or very much more massive object. So this is the reason why we can regard to a first approximation the sun as a massive, infinitely massive object sitting at the center of coordinates, the center of attraction, and the planets moving around the sun in orbits like a one body problem, because the center of mass of the Earth Sun system is essentially the coordinate of the sun itself. So it is essentially at the center of the sun, a little bit displaced from the center of the sun. Just as even in the Earth Moon system, the case of the Earth Moon system, the center of mass of the Earth Moon system is actually inside the surface of the Earth at any instant of time, because the Earth is so much more heavier than the Moon is. And in the case of the sun and the planets, the comparison is much, it's even more so. The sun is very much heavier than the Earth is. So this is how a general two-body problem, a central force two-body problem, gets reduced to an effective one-body problem moving in a potential, a certain potential V of r, a specified potential, from which we can find the equations of motion, this equation of motion, and attempt to solve this equation of motion. By the way, this equation here should be accompanied by another equation which is fairly straightforward here, which is m dr over dt equal to p, or rather I should write this as p over m. So you see, you have really a pair of equations for the unknowns r and p, and they are coupled to each other, and when I eliminate this, then I end up with an equation for the second derivative of r, which is the acceleration. So just to write that down here, this immediately implies if I differentiate p with respect to this, it's the second derivative here. So it says 1 over m d2r, sorry. So let's differentiate d2r over dt2. This is equal to, and multiplied by m here, that's dp over dt. This is equal to minus dvr over dr e sub r, and this is equal to some force here. So let's write this as f of r e sub r, and this gives us the familiar form of Newton's equation with which you are familiar, namely mass times the acceleration, the vector acceleration, is equal to the force, and it's, in this case it's a radial force. In the case of the sun, it's an attractive force. That's the next thing we have to do. This is the Kepler problem. So let's do that. In the case of the Kepler problem, which is planetary motion, we have this is equal to g times m mass of the sun times the mass of the planet. So I should write in my notation, we should write this as m1 m2 divided by the distance between the sun and the planet, little r here, with a minus sign. Okay. It's some constant divided by 1 over r. That's all we are interested in. So let me rewrite that in the form, let's rewrite this thing in a simpler form, which is dp over dt equal to the gravitational force. So it's some constant divided by r squared e sub r with a minus sign. Some constant which is the product of the masses, capital G, and so on and so forth. So this is the problem that one has to solve in the case of the gravitational problem where you have a planet orbiting around the Earth. And what was shown by Newton was that the solutions of this equation are such that this vector r, its locus is a conic section. So under all conceivable circumstances, the locus is a conic section always for any given initial conditions. For instance, suppose you have the center of attraction here and you have a planet, the initial momentum is in a direction which falls into this center of mass. Well, the planet will fall into this center of attraction, and that's it. So it's a straight line. On the other hand, if the center of attraction is here and the initial momentum is like this, it's possible that this gets scattered in that form and trace a hyperbola in space. There could be a case where here's the center of attraction and the initial condition is such that in a limiting case it traces a parabola of this kind. Okay. There's a specific value of the total energy for which this happens, by the way. And then there's a case where we have the center here and the planet traces out an elliptic path with the sun or the center of attraction at one of the foci. So we have all these possibilities, and this was Newton's great achievement, to essentially solve this analytically for all possible initial conditions and to show that the orbit in real space is always a conic section of some kind. Either you have periodic motion, in which case the particle executes an elliptic orbit in the general case, or a parabolic orbit, or a hyperbolic orbit. These two are open orbits and the particle essentially escapes. So these are the kinds of orbits that comets would trace. Typically they would execute, if the comet never returns, it would typically execute an ellipse, an orbit which is a hyperbola of this kind. Now it's interesting to ask under what conditions you have this intermediate case of a parabola, because if you think about it for a minute, you realize that an ellipse has two foci and a parabola is a limiting case of an ellipse when one of the foci moves away to infinity. Okay. So it turns out that in the case of this orbit, the energy of this particle whose coordinate is a little r and momentum is p is positive. In this case it is exactly 0, and in this case the energy is negative because it is a bound orbit. So these three cases are distinguished by the value of the energy of this effective particle of mass mu here, and that is what determines whether it is an ellipse or whether it is a hyperbola or a parabola or an ellipse, the parabola being the limiting condition that separates, the separatrix as it is called, that separates open motion, namely the hyperbolic motion, with a closed orbit, a periodic motion, which is the elliptic orbit. The next thing to do is to write, proving this, by the way, was non-trivial, and that was Newton's achievement. Today we know how to prove it fairly straightforwardly, but I am not going to go and solve these differential equations here, but rather we are going to assume that there are Kepler's laws, and my next task is to explain what the significance of these laws is, where they come from, and what they tell us in some sense. So that will be the next thing we take up.